Now we're going to turn to an important property of continuous functions, namely the intermediate value property. Let's say we want to join 2 points in the plane by the graph of a continuous function. If these 2 points are on the graph, they have coordinates a f of a and b f of b. And let's pick a value w that is between f of a and f of b. There is a line y equal w. What the theorem says is that if the graph of the function f joining these 2 points is the graph of a continuous function, then this graph is going to intersect this line y equal w. Therefore, there is a value c between a and b whose image under f is exactly w. The fact that each w between f of a and f of b is a value assumed by the function f is exactly the statement of the intermediate value theorem. This statement doesn't depend on the function f as long as this function is continuous. Here is another example, and you see that this graph would also intersect the horizontal line y equal w, this time in 3 different places. And this doesn't depend on the value w that you pick between f of a and f of b. As you can see, as we move this horizontal line around, we always have at least one intersection point with the graph of f. So, we obtain the intermediate value theorem stating that if we have a continuous function on a closed interval ab, for any value that we pick between f of a and f of b, there is at least one value between a and b that is sent by f on w. Now, continuity is essential in this statement, as we can see from this example. You see that here we have a function that has only one discontinuity on the interval ab, and this is enough to make the conclusion of the intermediate value theorem fail. So continuous is an essential assumption here. Now let's turn to an application. Let's say we want to see that the equation cosine x equal x has a solution. Note that the question is not to solve the equation, but just to justify that there is a solution. How to proceed? Let's consider the function f of x defined by cosine x minus x. Of course, showing that cosine x equal x has solutions is the same as showing that the function f takes the value 0. This function is continuous on the real line, and we can observe that, for instance, at pi over 2, the function takes a value negative pi over 2, therefore a negative value. And similarly at 0, the function takes a value 1, a positive value. Therefore, 0 is between f of 0 and f of pi over 2. And moreover, the function is continuous on the real line, so its restriction to 0 pi over 2 is continuous. Therefore, we are exactly in the situation described by the intermediate value theorem, where a is 0, b is pi over 2, and w is 0. So we can apply the intermediate value theorem to our function f on the interval 0 pi over 2 to the effect that there is some value between 0 and pi over 2 where the function f takes a value 0. But if f takes a value 0 at c, then c is a solution of the equation cosine x equal x. Note that what we have justified is just the existence of a value c between 0 and pi over 2, where cosine of c is equal to c. That doesn't tell us a lot about the value of c. So the intermediate value theorem is just an existence result. It doesn't give us much information on the value of c. However, we can still use it to try to solve this equation numerically, in other words, to find an approximation of the solution. Indeed, the way we have justified that there is such a C is by considering this continuous function cosine x minus x and observing that it takes a positive value at 0 and a negative value at pi over 2. And by continuity, somewhere between 0 and pi over 2, the function f has to take the value 0. So that tells us that we know that there is a solution and we know it up to pi over 2. The possible error is up to pi over 2. Now, if we want to do better, we could, for instance, take the midpoint, pi over 4, plug it in the function f, and we would get something negative. In other words, the function takes a positive value at 0, a negative value at pi over 4, so the intermediate value theorem tells us that there must be a 0 for the function f on this half of the interval. So now we have twice as much information on the value of c. Now we know that it's between 0 and pi over 4. If we want to do better, we can iterate this process. Take the midpoint, pi over 8, evaluate the function at pi over 8. We see that the function is positive at pi over 8. And that tells us that the 0 of f that we're looking for is in fact in this half of the interval 0 pi over 4. This process again can be iterated. The midpoint of pi over 8 and pi over 4 is pi over 8 plus 2 pi over 8, 3 pi over 8 divided by 2, 3 pi over 16. If we plug that in the function cosine x minus x, we're going to get something around 0.24, in other words a positive value, which tells us that the 0 we are looking for is in this half of the interval pi over 8, pi over 4. Iterating one more time, the midpoint of 3 pi over 16 and pi over 4 is 7 pi over 32. If we plug that in the function f, we obtain 0.08, so again a positive value, which tells us that the 0 must be in this interval between 7 pi over 32 and pi over 4. Of course, we could continue iterating this to get a better accuracy, but let's take a look at what we have so far. We went from saying that there is a solution somewhere between 0 and pi over 2 to the fact that there is a solution to our equation between pi over 4 and 7 pi over 32. So now the error in the estimate of the solution is less than 0.1. Well, this is not so bad in just a few iterations. Of course, if we keep iterating, at the next iteration we have an accuracy that is twice as good, and at the next iteration 4 times as good, at the next iteration 8 times as good, and so forth. This method to get an approximation of the solution of an equation is known as the bisection method, and as you can tell, it is simply based on iterating the argument of the intermediate value theorem that we use to justify the existence of the solution. This is all I wanted to say about continuity, and now it's time for you to do some homework on continuity.